All right, this is video 18 for the behavioral analysis series, and the last batch of videos covered sequences and series of real numbers. And just as a scope of where we are headed, we're going to be covering limits of functions for the next several videos, and then go into continuity of functions. We'll talk about the derivative, and what's in yellow or gold, it is depending on time. I guess really it's however amount of time I want to make these, but I will go into a small glimpse of the topology on the real numbers and then a brief overview of metric spaces. All right, so that's where we are headed. I think we'll first cover the limits, continuity of functions from how we are familiar with them from calculus course, and the derivative before we go into topology, where we try to generalize things, and then go into metric spaces. So a lot of these proofs apply for those as well. Okay. So these next bit of videos are going to cover limits of functions. So recall an E neighborhood is the set of x such that the distance between x and a is less than some epsilon. Or it's an open interval where the endpoints are a minus epsilon and a plus epsilon. So x is in that interval. All right, so x is less than a minus epsilon, or a minus epsilon is less than x, less than a plus epsilon. All right, so x is in, and as on you see in the picture, I have the real line drawn, and then you have the interval in green, and then a is, I like to call a the center. A is the center, and usually like to call epsilon as a radius. So epsilon is a radius. You're either going plus or minus some radius. All right, and in this definition, x itself may be equal to a. So that's what a neighborhood is. Now a cluster point is the following. So if you have a set A of the real numbers, and you have C as a real number, C is a cluster point of A if and only if for all delta greater than 0. The set A intersect, and then in green it has the delta neighborhood around C subtract out C. And that is the delta neighborhood around C, but with C taken out. So I like to call it a punctured neighborhood. So this I like to think of as the punctured neighborhood around C for delta as the radius. And I usually do MVHD as neighborhood. So you're going to have this set A intersecting this punctured neighborhood being non-empty. And that is what it means for C to be a cluster point. Okay, so said differently, C is a real number, is a cluster point of A. If for all delta greater than 0, there exists at least one point x in A where x is not equal to C, such that the absolute value of the difference of x minus C is less than delta. Note that the point C may or may not be a member of A, but even if it is an A, it is ignored when deciding whether it is a cluster point of A or not. Since we explicitly require that there be points in the delta neighborhood and the intersection of the delta neighborhood around C and A distinct from C in order for C to be a cluster point of A. And like I mentioned earlier, I like to think of this where it has the delta neighborhood around C and it has a subtraction sign. It's really just subtract out the point C from the delta neighborhood around C. I like to call that the punctured neighborhood about C. So here's a picture, and we have our neighborhood, punctured neighborhood in green. So we have the delta neighborhood around C, but you subtract out C itself. So that's why there's a open circle or open dot at C. All right, so it's just a fancy way of just take the point C out of the delta neighborhood. All right, so here's your standard just delta neighborhood around C. And then I just have that same thing. Except I don't include, so I take out C. All right, so C is taken out, so that's the punctured neighborhood. All right, instead of saying delta neighborhood around C, subtract out C, I'm going to be calling this punctured neighborhood around C. And the neighborhood I'll abbreviate NBHD. All right, so that's what it is. So you have a punctured neighborhood around C. And then for a cluster point, C is a cluster point if for all punctured neighborhoods around C intersecting A is non-empty. And then also in yellow, this explains it in words. The point C may or may not be a member of A, but even if it is, it's ignored when deciding if it's a cluster point of A or not. And we explicitly require that the points in the intersection of the delta neighborhood around C intersecting A be distinct from C in order for C to be a cluster point of A. All right, so some examples. This is a non-example. So if you had set A being just the values 1 and 2, this has no cluster points. For instance, if you pick delta to be 1/2, so all you're dealing with is the points 1 and 2 for the set A. That's why I have it in green. And now if you choose a delta being 1/2, then you're going to have for its interval 1 plus a half is 3/2, and 1 minus a half is 1/2. So then that punctured neighborhood around 1 in yellow, it contains members of the real number line that are not members of A. All right, and none of those are members of A. So none of these are in A. The same thing applies for, so when you intersect A with this punctured neighborhood around 1, its intersection is empty. So that means it's not a cluster point. 1's not a cluster point. The same argument can be true for 2. So recall that for a cluster point, it's a cluster point if it's for all delta. So as long as I can produce a single delta that makes it not true, then that makes it not a cluster point. So in this case, I picked a delta being 1/2 that just exists, just a single delta that contradicts what it means to be a cluster point, since it has to apply for all delta. And in fact, none of these 2 points that are in A are cluster points. So just to reiterate, so we have 1, 2. Let's focus on 2 this time. Let's choose the delta to be 1/2 again. And then so the punctured neighborhood around 2 with a radius of 1/2. So that's going to be V subscript 1/2. And then we usually put parentheses and then use a subtraction to say to take out. So take out the value 2, and that's going to be adding 1/2 to 2 and then subtracting 1/2 from 2. So 2 plus 1/2, so we have 2.5, and then 2 minus 1/2, 1.5. All right, so our punctured neighborhood is all of this, but we don't include 2. And so all of these values are values that are not in A. So none of these are in A. Right, because A is just 1 and 2. Since it's a punctured neighborhood around 2, and you can't have you're not including 2 itself anyways. So none of those are in A. So therefore, A intersect the punctured neighborhood with radius 1/2 around 2 is empty. All right, so that's an example where A has no cluster points. Let's consider the set A to be the set of 1 over n, or n's natural number. So that's like 1, 1/2, 1/3, 1/4, and so I have it marked in red dashes on the real number line. 0 is a cluster point of A. All right, so 0 is a cluster point because if you pick any delta, so any radius around 0, you form a punctured neighborhood around that. So you have 0 plus delta, 0 minus delta, so that's just delta, and then minus delta is your endpoints to the open interval. So between 0 and delta, there's always going to be a natural number n where 1 over n is less than delta, and that's because of the Archimedean principle. So there's always going to be members of A that are in the intersection of the punctured neighborhood around 0 and A. So all of these are going to be members in A. That intersect the punctured neighborhood around 0. So that means this is true for any delta. So therefore, 0 is a cluster point. And note that 0 is not an element of the set A itself. Now, if we chose our set, let's say B, to be the closed interval 0 to 1, 0 is a cluster point of B. And in this case, 0 is an element of B. So we choose any punctured neighborhood around 0, and that with radius delta, 0 plus delta. In between 0 and delta, there's members of B. So the intersection is non-empty. So in that case, 0 is an element of the set B, and it's also a cluster point of B. Now you can have the open interval 0 to 1, keeping the same, just choosing any delta around 0. The puncture neighborhood is going to contain members of C. Specifically, the members are from between 0 and delta. Okay, so those are some examples of sets. The first one was just a set of 2 values, 1 and 2, and that has no cluster points. The second one example was a set of 1 over n, and 0 was the cluster point. And the closed interval 0 and 1 and the open interval 0 and 1, these have 0 as cluster points, whereas 0 is an element of the closed interval from 0 to 1, and 0 is not an element of the open interval. So that's just some examples of what it means to be a cluster point. It's just any punctured neighborhood around that value has to intersect some set A. All right, so that's a cluster point. So here's a theorem. C is the cluster point of a set A if and only if there exists a sequence xn contained in A subtract out the point C where xn converges to C. So there exists a sequence xn, and it's contained entirely in the set A subtract C. All right, so to prove this, so let's say you did the forward direction, you would assume C is a cluster point. Then you need to show that there exists a sequence contained in A subtract C where xn converges to C. So the sketch, let C be a cluster point of A. That means for all delta, the punctured neighborhood around C, so that's delta, the delta punctured neighborhood around C, if it's any delta punctured neighborhood, that's B subscript delta parentheses C, so the delta neighborhood around Z, subtract out C, that's the punctured neighborhood. All right, so that's the punctured neighborhood around C, and as long as it intersects A, it's non-empty, then C is a cluster point, and that applies for all delta. Okay, so that's what we assume. So let the xn be a part of this intersection, since we know it's non-empty. So what does that mean? So then xn is an element of, so each sort of value of the sequence xn, so each xn is an element of the open interval C minus delta comma C plus delta, which implies the absolute value of xn minus C is less than delta. So we need xn to converge to C. So we need for all epsilon, there exists a capital N such that for all little n bigger than capital N, xn minus C is less than epsilon, since that's the definition of convergence for sequences. So we know this is a cluster point and it applies for all delta. So since it applies for all delta, let delta be 1 over n. Then for all xn and the open interval C minus 1 over n, C plus 1 over n intersect A, where xn is not equal to C, then we have that absolute value of xn minus C is less than 1 over n. So we can find in capital N. So for all little n bigger than capital N, the distance between xn and C is less than 1 over n, which is less than epsilon. All right, this is sort of the sketch of the main points. And here's a visual. And now we're going to go into the proof. All right, so the proof, we're going to assume C is a cluster point of A. We wish to show that there exists a sequence xn contained in A minus the A subtract out the point C, where xn converges to C. That's what we wish to show. So since C is a cluster point of A, then we know for all delta greater than 0, the punctured neighborhood around C intersecting A is non-empty. Since this is the case for any delta punctured neighborhood, let delta be 1 over n. So we know that A intersect the 1 over n punctured neighborhood around C is non-empty. So for any n, let xn be a member of this intersection of A intersect the 1 over n punctured neighborhood around C. So since that's for any n, we have that the sequence xn is entirely contained in A, since it's in the intersection of A in this punctured neighborhood. And it's in A, and it's where the members are distinct from C for all n. So we need to show that this sequence converges to C. So given epsilon, by Archimedean principle, we can find a capital N so that capital N is greater than 1 over epsilon. So that's for any real number epsilon by Archimedean principle. So then 1 over capital N is less than epsilon. So if little n is bigger than capital N, then we have 1 over little n is less than 1 over capital N, which is less than epsilon. And so we have xn is a member of A intersect the punctured neighborhood of 1 over n, punctured neighborhood around C, which means that we have the absolute value of the difference of xn minus C less than 1 over n, which is less than epsilon. And so this means that xn converges to C. All right, so that's that direction. Now the proof in the other direction. So we're going to assume there exists a sequence xn contained in A, subtract out C, and xn converges to C. We need to show that C is a cluster point of A. So for that, we need to let delta be arbitrary. So given an arbitrary delta greater than 0, we must show that the intersection of any arbitrary delta punctured neighborhood around C intersecting A is non-empty. Since xn, the sequence is contained in A, and xn converges to C, but xn can't be equal to C for all n, then there exists a capital N. So for all little n bigger than capital N, we have 0 less than the absolute value of xn minus C, less than delta, due to the convergence that we're assuming. And so xn is going to be part of any arbitrary delta neighborhood that's punctured around C intersecting A. So therefore the punctured delta neighborhood around C intersecting A is non-empty. Okay, so that's the proof in the other direction. Note that and it was mentioned that 0 is less than the absolute value of xn minus C less than delta. All that means is that you have xn part of the punctured neighborhood around C. It is a subtle difference from having absolute value of xn minus C less than delta, which means you have xn to be in the delta neighborhood around C, because you could have xn minus xn equal to C. So this allows for the possibility for xn to equal C, whereas this, because of the 0 less than the absolute value of that, then this guarantees xn is never going to be equal to C. All right, so that's another way of just writing that xn is a part of the punctured neighborhood around C. And again, this is my sort of terminology. I like to call it punctured neighborhoods so I don't have to keep saying this out loud. All right, so now we're finally on, so we got our idea of cluster points. Now we're going to go into limits of a function. So definition, let's say you're given a function f from set A to the real numbers, and C is a cluster point of A. F has a limit L in the real numbers. As for all x that approaches C, denoted, and this is from our calculus course, LIM, x, and then arrow to C, so limit x approaches C of f of x equals to L. If and only if, for all epsilon greater than 0, there exists a delta. So if 0 is less than the absolute value of x minus C less than delta, then the absolute value of f of x minus L is less than epsilon. So in words, I like to think of it as for all x in the punctured neighborhood around C. So that's this part, punctured neighborhood around C. We have a epsilon neighborhood around L, in which f of x is a member of. So for all x contained in, and then parentheses, I have the delta neighborhood around C, subtract out C. That's our punctured neighborhood delta around C. And notice the quantifier is exists delta. And that intersects A implies that you have f of x as a member of the epsilon neighborhood around L, and that's for the quantifier here is any epsilon. So it's going to be key to keep track of these quantifiers. So we have for any epsilon, that's given first, and then there exists a delta. So we say delta depends on epsilon. So whatever epsilon you give me, I am going to find a corresponding delta. Kind of like the sequences, for any epsilon, I find a value in index n. So visually, this is what we're looking at here. So we have all x in the intersection of set A, intersecting the punctured neighborhood around C. So that's basically all of this. And let me redraw it. Okay, so say this is our curve, and let's go with let's say A goes like from here. So we're only dealing with all of this. That's our set A. And now we're going to put a punctured neighborhood around C. So let's say C. Is right there. And then we go delta plus C, and then C minus delta. So let's say this is right there and right there. All right, that's the punctured neighborhood. And we're doing the intersection of this punctured neighborhood with the set A. Okay, so then that's what that means over here. And our x lies in that punctured neighborhood. So this is our x lies in this punctured neighborhood, which intersects set A. All right, so that's what's going on for the x-axis. So that's what's going on here. And that's what this is saying. For all x in the punctured neighborhood, the intersection of the punctured neighborhood around C with the radius delta. So for all x in that, that's the same thing as saying this. The 0 is less than the absolute value of x minus C, less than delta. Now on the y-axis, so our limit L is this, which corresponds to the y value of this point. And we have C as supposedly the x coordinate of that point. Now the point itself could be just a open dot. All right, so the point could not exist, but the limit can still exist. But the point is I have L as our limit, and around L, we have a epsilon neighborhood, which means we can go L plus some epsilon value, L minus epsilon. That's what's in purple. So L plus epsilon, so we have those dashed marks for L plus epsilon, and then this is L minus epsilon. And then f of x is contained in that neighborhood. Now here, we don't have a punctured neighborhood around L. Okay, so it's not a punctured neighborhood, it's just a regular neighborhood, epsilon neighborhood. All right, so given any epsilon neighborhood around L, we can find a corresponding punctured delta neighborhood around C that intersects set A. That's what it's going to mean for limit. So symbolically, we say, so for all epsilon greater than 0, there exists a delta greater than 0. So for all x and a, such that we have the 0 less than the absolute value of x minus c less than delta. So this means we have the x in the punctured neighborhood around C, delta puncture neighborhood. All right, and that's with radius delta. Then we have f of x, absolute value of f of x minus L to be less than epsilon. So that means we have f of x is in the epsilon neighborhood around L. All right, and that doesn't have to be a punctured. Now notice the negation of this statement, just to talk about that. So the negation of the statement is you're going to reverse the quantifiers. So for all epsilon, that becomes there exists an epsilon. And then for exists a delta, that turns into for all delta. And then for all x and a, it turns into there exists an x and a. And the negation of p implies q will become p and not q as the negation of that. So this is like our statement P, and this is our statement Q. So P implies Q. So this is going to be P and not Q. So we assume that we still have this punctured neighborhood. X is in this punctured neighborhood around C, but this is for all delta. And now we have the absolute value of f of x minus L to be greater than or equal to epsilon. That's the negation. And so that means f of x is not in the epsilon neighborhood around L. Okay, so just figured I'd go ahead and mention that. All right, so theorem. The limit of a function, if it exists, is unique. In other words, if you have limit x approaches c of f of x equaling L1, and then you have it equaling L2, then it has to be that L1 equals L2. All right, so for the sketch, we need, so we're going to assume a limit of x approaches c equals L1, limit x approaches c of f of x equals L2. We need to show that L1 equals L2. In other words, that the L1 equals L2 if the absolute value of their difference is less than any epsilon. So any real number epsilon, as long as that's true, then we can have L1 equaling L2. So we know from our limits, we know f of x minus L1 is less than an epsilon 1. And then f of x minus L2 is less than an epsilon 2. So we need this whole thing, L1 minus L2 to be, that needs to be all less than less than any epsilon. So we're doing a trick here is to add 0. And by adding 0, we're putting in minus f of x plus f of x. And then we can break it up using the triangle inequality. And then from the triangle inequality, we can manipulate each one of these. So we can manipulate each one of these since we know the limit exists for these ones. So it's for any epsilon, so any epsilon 1 for the first one, and then any epsilon 2 for the second one. we need the whole thing to be less than epsilon, so we can adjust them so that it can be epsilon1 to be equal to this arbitrary epsilon divided by 2. And then epsilon2, same thing, can be this arbitrary epsilon divided by 2. All right, that's pretty much how the proof's going to go. So here's the proof. Given epsilon greater than 0, assume that we have limit x approaches c equaling of f of x equaling L1, and limit x approaches c of f of x equaling L2. Right, and I'll put in parentheses what we're trying to show. I'm trying to show L1 equals L2, and that's if and only if the absolute value of the difference of L1 minus L2 is less than any arbitrary epsilon. So since we have that the limit of x approaches c of f of x equaling L1, we know for any epsilon1 neighborhood, so I'm just calling it subscript 1, so a subscript 1 neighborhood to correspond with L1. So there's any epsilon1 neighborhood around L1, there exists a punctured neighborhood delta 1 around C, which intersects A, which is a subset of the real numbers. Since this is the case, let our epsilon1 neighborhood be any arbitrary epsilon over 2 neighborhood around L1. So that if for all x in the punctured neighborhood delta 1 around C intersecting A, then we have f of x being in the epsilon2 neighborhood around L1. So said differently, let delta 1 be such that for all x in A, if we have 0 less than the absolute value of the difference of x minus c less than delta 1, then we have the absolute value of f of x minus L1 less than epsilon over 2. All right, so that's using the fact that we know that limit x approaches c of f of x equals L1. All right, so we're just using the limit definition for that. We're going to do the same for L2. So that is, let delta 2 be such that for all x in A, we have that 0 less than the absolute value of x minus c less than delta 2, then the absolute value of f of x minus L2 is less than epsilon over 2. All right, that's using our other assumption. So we need to guarantee both of these cases. So we want both of these cases to occur, so we're going to choose delta to be the smaller of the two punctured, or the radius. Let delta be the smaller of delta 1 and delta 2, where delta 1 and delta 2 are two punctured neighborhoods around C. So we want it to guarantee the limits for both, so we need to use the smaller radius. So pick delta to be the min. So for all x in A, we have that if 0 is less than the absolute value of x minus c less than delta, then we have the following. The absolute value of L1 minus L2 equals, and then this is where we add 0. And then we use the triangle inequality to get L1 minus f of x plus the absolute value of f of x minus L2. And each one of these is less than epsilon over 2. So we add epsilon over 2 plus epsilon over 2 to get epsilon. So therefore L1 equals L2. So the limit is unique. All right, so that's the theorem, and this was the proof for that theorem. The next thing is the sequential limit theorem. And it says that the limit as x approaches c, f of x equals L if and only if for every sequence xn, that's a subset of A, take out C, so A with C taken out. If xn converges to C, then f of xn converges to L. All right, so this is an if and only if proof. All right, so for the proof, we go the forward direction. We need to show that for all sequences xn contained in the set A subtract out C, we have that xn converges to C, then f of xn converges to L. So that is, we need for 0 to be less than the absolute value of the difference of xn minus C to be less than delta, implies that we have the absolute value of the difference of f of xn minus L to be less than epsilon. But we know that if we're going in the forward direction, we're assuming the limit of f of x equals L. So then we know that for 0 less than the absolute value of x minus C less than delta, we have the absolute value of f of x minus L to be less than epsilon. So by Archimedean principle, we could say there exists a capital N where capital N is bigger than 1 over delta. So then 1 over capital N is less than delta. Then we have for all little n bigger than capital N, 1 over little n is going to be less than delta since it's less than 1 over capital N. All right, so this is going to be sort of the structure, now the actual proof. So we're going to assume we have the limit f of x as x approaches C to equal L. Pick any arbitrary sequence xn to be contained in A subtract out C, such that xn converges to C. Given epsilon, because we're going to use the fact that we have the limit of f of x as x approaches C to equal L, so given any arbitrary epsilon, let delta be such that if we have 0 less than x minus C, absolute value of that to be less than delta, then the absolute value of f of x minus L is less than epsilon, just using our assumption. Using this same delta, we know by Archimedean principle there exists a capital N natural number such that capital N is bigger than 1 over delta. Then 1 over capital N is less than delta. So if little n is bigger than capital N, which is bigger than 1 over delta, then we have 1 over little n less than 1 over capital N, which is less than delta. Hence, if the absolute value of xn minus C is less than 1 over n, which is less than delta, then we have the absolute value of f of xn minus L to be less than epsilon. All right, so that's the forward direction. And we basically showed that we assumed that we had the function f of x, its limit as x approaches C to equal L, and we proved the sequence version of that. If the sequence where xn is contained in A subtract out C, if xn converges to C, then we prove that then f of xn converges to L. Now in the other direction, it's going to be a little bit, it's going to be unique in the sense I'm going to use a contraposition type of proof. So in the backwards direction, where the statement P implies Q, what that is, our P and Q. Our P is the statement, this time we're going to have a sequence xn and the set A subtract out C, where xn converges to C, then f of xn converges to L. This is what our assumption is going to be in this direction of the proof. This is our P. Then we need to show that the limit of f of x as x approaches C equals L. This is our Q. So the contraposition of that would be not Q implies not P. All right, so this is not Q implies not P. So not Q would be the limit as x approaches C of f of x does not equal L, implies, and then I took the negation of P, where P is what I underlined in red. So the negation of that would be there exists a sequence xn in A minus the value C, where xn converges to C, but f of xn does not converge to L. All right, so that's our not Q implies not P. Now, what does this mean? So what that means is there exists an epsilon. So for all delta greater than 0, there exists an x, where 0 is less than the absolute value of x minus c less than delta, and we have the absolute value of f of x minus L to be greater than or equal to epsilon, because that's the negation of what it means to be a limit. So recall that limit x approaches c of f of x equals L means for all epsilon, there exists a delta. So for all x in A, we have 0 less than the absolute value of x minus c less than delta implies the absolute value of f of x minus L to be less than epsilon. That's what it means for the limit. So if we're going to make that the negation of that, because that's going to be our not q in this case, that means we change these quantifiers. So this changes from for all epsilon to there exists. This changes to for all delta. This changes to exists in x. And then this changes instead of p implies q, this would be p and not q. So this would be this and f of x minus L to be greater than or equal to epsilon. All right, that's what it means for the limit of f of x as x approaches c to not equal L. All right, so that's what we're going to assume is that negation. And then we're going to use that to prove that the negation of p, and in that case, there exists an xn where xn is an a subtract c, where xn minus c is less than delta, and f of xn minus L is greater than or equal to epsilon. All right, so if we assume it's not true that the limit x approaches c of f of x equals L, then it's not true that there's for all. So if we assume it's not true for this, assume it's not true for that, then it's going to be not true for this. All right, so that's how the structure of the proof is going to be. And by doing those, assuming it's not true for each one of those, we use the negations of those statements. All right, so again, backwards direction, we needed to show, assuming that for all xn and a subtract c, where xn converges to c, then f of xn converges to L. That's our statement P that we're assuming. That implies the limit of f of x as x approaches c equals L. That's our Q. So if we can do proof by composition, we would prove not Q implies not P. Not Q would be the limit of f of x as x approaches c does not equal L. And that means there exists an epsilon for all delta, there exists an x, where this x minus c thing is less than delta, and f of x minus L, the absolute value that's greater than or equal to epsilon. That is what it means for the limit to not be f of x to equal L. All right, that's our not Q. So we're going to assume that and then show not P. Well, not P would be the negation of P. And so the negation of that would be there exists an xn and a minus c, where the xn minus c is less than delta, and f of xn minus L is greater than or equal to epsilon. All right, so if we can show that, then we could say, well, by contraposition, P implies Q. Okay, so proof by composition, assume the limit as x approaches c of f of x does not equal L. Hence, we have that there exists an epsilon for all delta, there exists an x, a number x and it's an a subtract c, where the absolute value of x minus c we have is 0 less than the absolute value of x minus c less than delta, and f of x minus L, the absolute value that's greater than or equal to epsilon. All right, that's what it means by limit of f of x to not equal L. So then for such epsilon, then for each natural number n, choose delta to be equal to this 1 over n. So we know this is the case for all delta. So why not just pick delta to be 1 over n? All right, so since that's the case, we know for all delta, choose delta be 1 over n. So therefore, there is some sequence xn and a, subtract out c, where 0 is less than the absolute value of xn minus c, less than 1 over n. Since we have this, then it's true for it to be for the sequence of xn minus c to be less than 1 over n for all n. And we have that f of xn minus L is greater than or equal to epsilon. Hence, we have for all xn and a minus c, where xn converges to c, but f of xn does not converge to L. Therefore, we have shown if limit of f of x equals L as x approaches c is not true, then for every xn sequence that's contained in a minus c, if f of xn converges to c, then f of xn converges to L is not true. So by contraposition, we would say then for every sequence xn in a minus c, f of xn converges to L whenever xn converges to c is true, then the limit of f of x equals L as x approaches c is true. All right, so that's a mouthful. Hopefully that makes sense. Maybe pause video and write down this proof and contemplate on it. But it was really just doing a proof by contraposition. Okay, so what I think I'll do is start the next video with working out some examples. So we've covered a good bit of terminology. We first talked about cluster points, and that involved talking about what a punctured neighborhood is. And then we brought in the form or the idea of a limit of a function. Then we talked about if the limit's unique. And then we did a proof by using the sequential limit theorem. All right, so I think that's a good stopping point. So for next video, I'll start out with these examples.